Welcome back to numerical methods. Today we're going to start our fourth unit, which is talking about line fitting. We're going to start out with the basics of linear regression. So how do we fit just that simple y equals mx plus b line? Just as a review, last time we finished up with simultaneous equations, talking about Gauss-Seidel-Jacobi methods, how we can assess how diagonal dominance will tell us if we are going to get a convergent solution, and how relaxation can improve convergence of iterative methods. And then we solved non-linear equations using successive substitution and the Newton-Raphson method. Today, with our new unit, we're going to start off with a brief review of statistics. This is going to help us formulate our line fitting problems. Then we'll talk about calculating slopes and intercepts for a line to best fit the data. Then we'll talk about coefficients of determinants and error estimates for that fit line. And then we'll talk about how we can take equations which are not linear and make them linear, and therefore how we can fit those lines. And lastly, we'll apply this to a problem in Matlab. Let's start our discussion today talking about distributions of data. Here along the x-axis, I've plotted some series of data, so maybe a series of data called x, and on the y-axis, I've plotted how frequently that number came up. A lot of times, data falls within what's called a normal distribution. I'm sure you've seen this sort of graph before, from everything from grades in, say, classes to looking at how patterns fall along the line. It's characterized by this peak and then shoulders that come down. So once again, this is called a normal distribution. And a normal distribution has some information that tells us about the location of the data. So location, which says where along the x-axis does the data occur, and then also the spread of the data. So instead of telling us where the data is localized or maximal, this tells us about how wide the data breadth is, right? So say if I flip a whole bunch of coins, right, I have equal chances of getting heads or tails. But if I flip only 3 coins, how often, or 4 coins, how often do I get 2 heads and 2 tails, and how often do I get other things, right? So that spread tells us how fine we are centered on that location, or how wide we're spread out along that y-axis. So within that normal distribution, we have several different ways to measure the location. The first one being the arithmetic mean. So this is the mean that this is the average essentially that you've grown up using. Here we take the sum of each point, in this case y, we sum them all together and we divide by n. This is going to give us our average or our arithmetic mean. We can also talk about a median of the data. This is the midpoint of the group. What we do here is we line up the values from lowest to highest, and then we find which data point is exactly halfway down the middle. So which splits the number of data to be in the lower half, which value splits it into that upper half. The third type of data is the mode. This is the case where we look at which value of x has the most occurrences. So if I sort of bring back that idea of that histogram from the previous slide, we may see some sort of Gaussian-like or normal-like distribution, but that doesn't necessarily mean that that's the biggest location, right? So maybe this is the data, but at this one point, say here, it has the most number of occurrences. So this is the frequency. Next, this would be the mode, right? Which value has the most occurrences? Just like looking at the measure of location statistically, we can also put some numerics to measure the spread, so how wide this is. We have three different measures of spread. The first being our standard deviation. Our standard deviation is going to have this SY nomenclature, and it can also be written out as a sigma. And so what the standard deviation is, it's the square root of the deviation of each individual y from the average divided by the number of degrees of freedom. So this is the degrees of freedom, and that ST is the sum of the squares of the data residuals. Sum squared residual. So what does that mean in general? So what we're going to do is we're going to take each data point, IY, subtract off the mean, and square it. Essentially looking at how far away from the mean is each individual point Y. And then we can take that square root over the number of data points minus 1. So how many degrees of freedom we have. We can also look at what's called the variance. So the variance is merely the square of that standard deviation. So the formula looks very similar. We take the sum of each data point minus the average squared over n minus 1. And then you can write this out in several different ways. Right? We can distribute that sum through, so we have a sum of each individual data point minus the sum of each data point squared over n, all over n minus 1. So just a few different ways to write that same equation. The last measure of variance that we'll bring up is the coefficient of variation. The coefficient of variation being the standard deviation over the average times 100%. Right? So what percentage of the mean is my standard deviation? Let's put this into practice and extract some of these data characterizing statistics from some real life data. So let's specifically calculate the mean, median, variance, standard deviation, and coefficient of variation for a set of data that measured the thermal expansion of steel. So here we have 24 data points just organized in this system. We're going to go through and we'll calculate each of our statistical variables, looking at the location and the spread of our system. Okay, so for the mean, remember we're going to sum up each individual value and divide by n. So I'm not going to go through doing out the arithmetic, but in essence, I'm going to take 6.495 plus 6.665 plus 6.755, etc., all the way down till I get 6.85. Add them all together, which will give us 158.4. Right? So this is my sum of my y. Put 158.4, and I have 24 entries. So my average is 6.6. I can do this sort of a similar process. I can take each of my data points and sort them from smallest to largest, and then go through and find which one is in half. When I go through and do this, I find that I have 12 data points, 12 data points which are lower than 6.05, and 12 data points which are equal to 6.615 or above. So this sort of splits it in half. So for the median, what I need to do is I need to take the average of those 2 points, to find that value, and that gives me 6.61. In this case, the average and the mean are quite similar to each other, but this doesn't necessarily have to happen. Let's say, for example, I had a really large number or a really small number. The mean is going to be more affected than that median. Let's look at the variance. So in order to calculate the variance, we need to know what is the mean and the difference from the mean of every point. Here I've taken each individual value and I've lined them up. So here are all those different y values that we had before. And we can take that mean value that we calculated, so I minus 6.6 squared, and I can put that in this column. So all I'm doing is taking each individual value. So here in that first case, 6.395 minus 6.6, and then squaring that value. So I've come down here, done that for each individual element. When I do this, I find that that I can take each of these and then I can sum them up. So here I've gone through there and I've summed those values together. This gives me a value of 0.217. Right? So this is just taking all those values, summing them up. Next, I take my 24 points minus 1 to get 23, and I can then just calculate 0.009435. Right? So this is our variance. The standard deviation is nice because if you remember, the standard deviation, SY, which is our sigma, is just that variance taking the square root. So we can take that 0.009435, take the square root, and that gives us 0.097133. And then finally, we can go in and calculate my coefficient of the variation, which remember is our standard deviation over the mean times 100. So my standard deviation was 0.097135. My average was 6.6 times 100% is 1.47%. Well, my coefficient of variation is saying that that variance, the spread of this values is very small, or is only 1% of that mean. So we can really trust this data to be highly localized. This may not always be the case, right? If my coefficient of variation were large, say 20%, well, that's meaning that what we sort of see in that spread of the data could be 20% of the mean, right? We're really seeing that data is quite noisy. Good. So what you'll also notice is a lot of these the statistical pieces that we've seen are going to involve summing up these large sets of data. Right? Here I had to do relatively simple math to calculate the average, right? All I needed to do was sum up 24 numbers. However, this can get very tedious to do by hand, whereas a computer doesn't mind calculating 24 or adding 24 numbers together. Similarly, calculating the variance required taking subtracting one number from another 24 times and then squaring the result, right? Not a lot of in-depth thinking, but very tedious to do by hand. So this is actually one of the places where computers are going to come really in handy, because the Matlab will calculate a lot of these summations for us. And not only the summations, but it'll calculate mean, median, mode of our various data. So let's see how we're going to do that. Before we go in and do this in Matlab, I just want to touch on some of the functions that Matlab is going to have to help us. So the first set is just mean. It's going to go in and calculate the arithmetic mean. Same thing for median. It'll go in and calculate the median on a vector and the mode. Right? Mean, median, mode of any sort of vector. Same thing, we can get the minimum and maximum of a vector, and of course we can calculate the variance or the standard deviation of that vector. If I provide a matrix instead of a vector, Matlab will give us on a column by column set. So let's say I have, I don't know, 1, 2, 3, a 3-column matrix. If I type in mean, Matlab will give us return 3 numbers, the mean of each of our given columns. Okay, cool. Let's go in and try this out in Matlab. Here I am in Matlab. I've started out by just providing a random set of numbers that are surround S. Sorry, a random set of numbers in a variable called S. So let's go in and just see how these different commands are going to work. So I can use the mean command and find that my average, or my mean, is just under 20, 19.89. We can do the same thing with the median, the mode, and find the min and the max. So min of S is at 19.19. What you'll notice is the mode and the minimum are the same, right? In this data set of S, there's no repeated number. So MATLAB's just picking the lowest value. I can do the max, it gives me the max. Right? So we can get all these nice statistics on the location, and then we can extract information on the variance, or the spread of the data, using var for variance of S, so 2, and the standard deviation of S, which is 1.4, the square root of 2. Right. So we can get all of this information out of MATLAB. The other thing that we may want to do is see a histogram of the data. In this case, all I need to do is type in hist of S, and a image of the histogram will pop up. Let me reshare my screen so that you can see the produced histogram. So here we can see that that histogram. It's taken those data that I've generated, and it's put them into several different bins. In this case, each bin is 0.5 in width, and it counts up how many of those 10 data points reside within each bin. In this case, there's 2 data points that are less than that are less than 18.5, and then all the way up, and we see our last data set includes 21.5 to 22. So this histogram column will produce that histogram for us. If I go back into MATLAB, I can extract information out of that histogram function by saying things like how many elements so n will fall in the center of some number of bins, x, hist x, where we want to, where we could put in, say, 10 bins. We can put in 10 bins here. Right? And so in this case, we see that the center of each bin is at these values that are stored in x, and how many data points in each bin are stored in n. So just to review, we have three sort of options with our histogram call, that hist command. If I put in my vector of data, s, and then a vector x that can, then the histogram will return the number of data points in s that are in bins centered on that value x. Conversely, if I set just a single number in m, Matlab will return not only those how many data points belong to in each bin, and it'll give us the center of a bin. If I don't ask for any return, so I don't include this, n equals, Matlab will just print out that histogram, just like we saw when we were working in Matlab. Now that we've reviewed some of our statistics, hopefully it's been a review, let's put this into action and use it to extract fits to lines. We're going to start our discussion of fitting lines with least square regression. In essence, we're going to use error, and specifically the square of an error, to fit a line or regress a line. So we'll get into what each of these terms means in a second. So in essence, given a set of x data and a set of responses y, I can plot each individual data point. But we often want to see which line is going to fit best to this, because we may have cases where data was taken at, say, only 8 points, but I want to be able to calculate some value y at any point along that line. Right? So in essence, we want to find this red line here that best fits the data. It best represents what's happening. And we want that line to have, this case, in linearly squared, we want it to be a straight line. So we want it to have the form y equals a times x plus b. Now, what we are in essence going to do is we're going to look at the error between each point. So here's the data point, here's what our fit would give us, and we want to find out how much error, how wrong are we if I use this point along the line. And then what we're going to do is we're going to try to minimize, we're going to change A and B such that E is as small as possible. If I just look at E, I can end up having data that cancels, right? So here's, maybe this error is positive, this error is negative. So if I just look at each error individually, or if I look at the total errors summed all together, these two may end up canceling each other out. So what we want to do is we want to look at the square of that error. By squaring that error, we're removing any issues that might come from some error being positive and some error being negative. let's put this into some mathematical terms. So here we have the equation of a line that we want, and then I'm also going to include an equation for the error. So our error is the value of the data at any point xi minus what we would get from that fit. So all I'm doing is taking the individual data point minus the line predicted data point. So this is our error. And the sum of squares of our error is just taking the error of each data point, so say maybe EI, squaring it, and then summing it for each individual data point. If we want to minimize our error, right, we want to minimize the error, we just need to recast this problem as a calculus problem, right? Here I have a function, SR, right, which we can say is I equals 1 to n of xi minus a, sorry, yi minus a, xi minus b. Right? Here's an equation, and I want to minimize my error. I want to make the error as small as possible by changing a and b. Put this in other words, I want to find, put this in other words, I want to find the location where my derivative with respect to my sum of my errors with respect to a is 0, right? When I take the partial derivative of any function with respect to a number, I find either a maximum or a minimum. I want to do this not only with a, but I also want, which is our slope, but I also want to find the best intercept. So I have to just take the derivative of my sum of squares with respect to b. And so we've recast this problem of how do I fit a line into a calculus problem. Let's take this through step by step. So here we have the equation that we want to minimize, and then we have we have our location of the derivative, or sorry, the location of that minimum can be found when my derivative of SR with respect to A is 0, and my derivative with respect to SR with respect to B is also 0. So let's take this through. So if I take my derivative with respect to A, so let's put this here, partial SR, partial A, I'm really taking this piece and taking the partial derivative with respect to A. So I can go through each term. Remember, when I take the partial derivative with respect to A of my sum yi minus a xi minus b squared, I have my chain rule, so that is equal to twice what's happening in the parentheses, a xi minus b times the derivative of what's happening inside that parentheses. The only location that I have a is where it's multiplying by x, so that derivative is xi. Okay, and so since I have all these, since I'm doing this again and again and again, I still have that summation. So this gives me a final equation shown here. I'm not going to go through the math because it's a little bit tedious, but I'll show you what the end result is. So here we have the derivative, the partial derivative that we're interested in. We can set this equal to 0. Then we can take this system, or one big long equation, and solve for a. When I do that, I end up with this equation at the bottom. It says that my a value, so my slope, is equal to n, so the number of data points, times the summation of xi, yi, minus the sum of all of my xi points multiplied by all my yi points. So I'm going to point this out and really make sure that you're noticing this very subtle difference. So here I'm taking xi times yi and summing up the products. Here I'm taking the sum of xi times the sum of yi. So very similar but slightly different, right? I multiply first, then sum, and here I sum, then multiply. On the bottom, we have a very similar looking set. Here I have n times the sum of xi squared minus the sum of xi that is then squared. So once again, the difference here is in that first term, we square, then sum, and here we sum, then square, right? So the biggest place that people make mistakes are trying to, they end up doing the same thing twice and they get 0 on both places. So in both cases, it's n times multiply first, then sum, minus sum, then multiply. Okay. So we're going to then do the same thing for our intercept. We're going to solve for that partial derivative here. So if I take this through, if I take partial SR, partial B, multiplied through, I once again pull that beginning piece, that squared down. So this is xi minus a xi minus b times the partial derivative of that inside. It's just 1. Okay. So just write this out a little bit nicer. We have my derivative of SR. So the derivative of my squared error with respect to b is twice times the sum of yi minus a xi minus b, and I'm going to set this all equal to 0. Now I'm going to do the exact same thing where I'm going to solve this time to isolate b on the side. And once again, I'm not going to go through and do all the math, do all that algebra, but it ends up being the sum of yi over n minus a times the sum of the xi values over n. So taken together, I have an equation. I first will solve for a using the equation on the previous slide. I can then substitute it into the equation here for b, and I have the fit of my line that's going to give us the minimum error for the entire system. So in general, in addition to wanting to know exactly what the fit is, we often want to know how good the fit is. So how well does that line represent the data as a whole? In order to do this, we're going to define 2 sets of variances. First, the sum of errors squared. So that SR that we've talked about on the previous few slides. So what is the expected value from the line minus the actual value? And then we want, we also want to define the second variance. So ST, which is going to be the variances of my y's. So this is that just variance of my y values again, just like we saw at the beginning of the lecture. So our coefficient of determination is going to be set by is going to be called r squared, and it's going to be the variance in y, so how much variabilities there in y, minus my error all over the variation in y. Put another way, what we're really asking with R is how much variance is removed by fitting a line. Right? So before I fit a line, right, if I just take that average value, how much variation do I have? So that's, remember, ST. And each of these pieces, right, it can be considered an error. If I just take that mean. If I then fit the line, I can calculate how much error there is on each data point here. That's that SR. So I'm really taking that, that percent error, how much of this variance can I eliminate? So when I go from here to here, how much of that variability goes away? Right? How much do we sharpen that spread? How much can we squish it down? And it's all put together in this value R squared. You'll see this a lot when you look at data in papers or in textbooks, where they'll fit a line and they'll show, y equals mx plus b, and then they'll show an R squared value. So this is exactly what that R squared is. So what does this R squared mean? Well, R squared, once again, is the percentage of the original uncertainty that's explained by the model. If we have a perfect fit, so all the data falls exactly along that line, we end up having R squared equals 0. Because S of R equals 0, we have no error. So we have S of t over S of t, R squared of 1. If R squared is 0, there's no improvement in the data, right? I have just as much randomness as before. You rarely see this case. You can also have a case where R squared is less than 0. So this means that the model, in this case, we're just talking about a straight line, is actually worse than just taking the average of the data. Right? So if I have R squared between 0 and 1, the model's improving or minimizing the error. If it's less than 0, I'm increasing that average error. I now want to look at an example. Here, I want to see how the velocity of, say, an object correlates with the force on that was applied to that object. So here I have my velocity, that's going to be my x, and here I have f, which is going to be y. And I've plotted those terms here in this graph on the right. To find my best fit line, I need my A and my B. So here I've just pulled forward those equations, and it tells us that I need to know the product of x and y and my x squared, as well as the sum of each of those, of x and y. So what I need to do is go in and calculate x squared and xy. So here in this third column, I've just taken each value of x and squared it. So 10 goes to 100, 20 goes to 400, 30 goes to 900, etc. In that fourth column, I also need x times y. So here, 10 times 25 is 250, 20 times 70 is 1400, etc., all the way down. I've also gone in and summed each of the different columns at the bottom. So I've taken all the x values, summed them together, all the y values, summed them together to get a little more than 5,000, summed the square values together to get roughly 20,000, and summed x times y to get 312,000. With these values, I'm now ready to calculate my A and my B. Okay, so first we need to know how many values we have. Well, we have 8. We now need my xy, my sum of xy. Well, that's this 12,850 minus the sum of the x's. Well, that's 360 times the sum of my y's. That's 5,135 all over n times the sum of x squared. The sum of x squared is 20,400 minus the sum of x squared. Well, the sum of x is 360, and I square that. So if I put this all together, this gives me 19.47, and then some additional decimal points. For my b, I can calculate my average y. Well, that's the sum of each individual piece, 5135 over 8 minus a, which is 19.47 times the average x, which is 360 over 8. I do out the arithmetic and I get negative 234.28. Right. So my estimate for the force is the slope. So 19.47 times the velocity minus the intercept, which is 234.28. This gives us the slope of my line. We still probably want to know a little bit about how good our fit is. In order to do this, we need to go in and calculate R. So this means calculating the variance in the y data and calculating that associated error. If you can see from that ST value, we take each data point minus the average y and square it. So this is going to come in, I'm going to do this in this third column. I'm going to take each yi minus the y average, sum them, sum it all up. And if I do that, I end up getting 1808297. So once again, this is the average y minus each y data. So I'm just sum them all up in this column. Then we're going to do my SR. And so we need to know sort of what my expected value of A minus, let's call this B minus A1x. Here I've just taken that A and the B from the other side, put them together in here, and then I can subtract off the associated y for each value, square it, and then sum that value. So if I do this, I get 216,118. Right? Then I'm ready to calculate my R value. It's simply 1808297, bringing down ST minus 216,118, all over 1808297. Okay, so if I do this out, this gives me 8805. In essence, almost all of the variance in this data, in that y data, can be explained by the line that we fit. we're quite close to 1. So we can say that we have a good fit from the A and the B that we calculated previously. So these methods, so this more or less covers our linear regression model. So we can calculate the slope, the intercept, as well as the goodness of the fit. And this is going to be very powerful. However, many problems that we are going to encounter in chemical engineering or engineering sciences in general are not simple linear relationships. This is what we're going to cover the rest of the class and for the rest of this unit. The most easy way we can approach addressing nonlinear relationships is if we can turn those nonlinear relationships into linear relationships. As you saw in the previous few slides, while possibly tedious in doing all those multiplications and summations, the ideas behind linear regression aren't necessarily super complex. So tedious, yes, but doesn't require any minimization algorithms, right? We can just do that all by computation. And we can take many types of equations, such as exponential equations, power-based equations, or in chemical engineering, saturation growth rate equations, and we can convert them into a form that linear regression can be applied to. So we can change out of one form of an equation into another form that's going to be easier to solve. So let's look at 3 different models of systems. So here we have our exponential y equals alpha e to the beta x. And we can think about how we might want to turn this into a linear equation. Well, what you'll notice is the thing that's holding us back from linearizing this equation is this exponent. We can get rid of that exponent, of course, by taking the natural log. So if I take the natural log of both sides, I have the natural log of y equals the natural log of alpha plus beta x. Here, I now have a system that's linear in x and related a variable to it. In this case, it's not y, but it's the natural log of y. I can do the same thing in a power equation. So if I maybe have x to a beta power, I can pull this piece, that beta down by using the logarithm. So if I take the log of y, and then if I get log of y. If I take the log of alpha x beta, remembering our power for the logs, I have the log of alpha plus beta log x. Once again, I have a linear equation here, right? I have just one variable beta times a variable that's log of x. So this is linear with respect to this log x value, right? And so the last thing that we can look at is the saturation growth rate. So this one may not be quite as obvious how I can linearize it. But let's take the inverse of both sides. So let's take this to the -1 power and this to the -1 power. So if I take that inverse of y, I get 1 over y equal to beta plus x over alpha x, which will leave me, if I split the pieces up, beta over alpha times 1 over x plus 1 over alpha. Right? And so now I have this term 1 over x with a single variable in front and a single grouping of constants over here. So I have another linearized rate. So what does this look like? So here I've taken that exponential function, and when I do that transform using the natural log, I end up with the natural log, the natural log y is linear with respect to x, where the slope is beta and the intercept is the natural log of alpha. This is going to come in handy as you get into reaction kinetics, because a lot of things are going to have this exponential order. We can take another look in this in the x to some sort of power. So here I plot log of y versus log of x. So I would take the log of every single data point x, every single data point y, and when I plot them against each other, if I find a straight line, we know that it's got this form where the slope is that exponent, and log of a2, the intercept is equal to log of a2, so that intercept is related to what's out in front of that x. So lastly, we had that more complicated version, more complicated formula. Here, if I plot 1 over y versus 1 over x, and I have this straight line, I once again know that I'm operating on a saturation growth type model, where the intercept can be related to this constant alpha, and then the slope beta over alpha can be related to this denominator term. Let's use these linearizations to solve a chemical engineering problem. We're going to look at a series of enzymatic reactions. Remember that enzymes are essentially organic, proteins that are going to catalyze the rate of a chemical reaction. Where we're going to take the reactant, also called the substrate in biological systems, and convert them to some sort of product. In most biological systems, these can be described via the Michaelis-Menten equation, where V is going to be my initial reaction velocity, so how fast is the reaction going, and that's related to the maximum rate of the reaction, the concentration of the substrate or the reactant, and then this Ks term, which is called the half saturation constant. Overall, these reactions are going to look like this, where I have this initial increase in my rate that will then plateau as the amount of substrate increases. So if I have a lot of substrate at the beginning of my reaction, I'm not going to go infinitely fast. I have sort of this plateau at my maximum reaction rate. And I can do this for my first order Michaelis-Menten model, and I can write out a second order Michaelis-Menten model. In this case, in the second order case, I have this squared term up at the top. They're both going to have the same value at this point of that half saturation constant. So they're both going to go half the maximum velocity at this Ks value. So we're going to take this, look at some data, linearize these two equations into the proper form, and then use Matlab to solve out for these different variables. And we'll see then how the data fits the two different models. From looking at these two different models, then we'll be able to tell whether this particular data set better fits the first order model or the second order model. First, let's look at some data. Here we've got a series of data that's been collected where we have the initial substrate concentration and we have the initial reaction rate. What we want to know is what is the maximum rate, Vm, and what is the half saturation constant, Ks. So in order to do this, we're going to use linear regression. You may be saying to yourself, well, Professor Muick, we don't know how to deal with such complicated equations, but we really do, because we're going to use that linearization profile. So if I take my first order model, we can do that idea where we flip, we can take the inverse of both right and the left-hand side of the equation. When we do, we get 1 over that reaction rate is equal to 1 over Vm plus Ks over Vm times 1 over S. Here's going to be the idea. We're going to take this 1 over V, and this is going to be set equal to our X. We're going to take this 1 over S, set this is going to be our X. So in essence, this Ks over Vm, well, this is my slope. This 1 over Vm, this is going to be my intercept. All right, I'll see you over in Matlab, and we'll see this in action. Okay, now that we're in Matlab, we're ready to input our data. So I've gone ahead and done that already. So you can see that I've put in that data for the S, so the substrate concentration here, and my initial velocity. Now, what we want to do, if you remember, is find 1 over S. So we could say S1 is equal to 1 over S. Remembering, of course, that we need to do it element by element so that we, because we're doing that division. So I can do this, and I now have the inverse of S. I can do the same thing for V, so V may be 1, and we can set that equal to 1, the inverse of V1 dot V. We can get all of this data. I can now go ahead and conduct the linear regression. Now we can use MATLAB's built-in polynomial regression model to figure out what the values of my polynomial are. So here I'm just going to create a value p and set that equal to the MATLAB call, so polyfit. Then simply my x, so which we're doing that substrate fit, and my y, that's v1, and the order that we want, well, we just want a linear fit, so we put in 1. Right. When I hit enter, I get my 2 values for p, which will tell me the values for my various fits to this curve. Okay, so now that we have my fit values, let's go back to MATLAB and go back to PowerPoint, and we can see how we can change these slope and intercept into something that's more directly understandable. Once we have the fit polynomial values, so just to write this down again, we have our slope, which is that first value that came up, so 16.4022, and our intercept, which was the second value, so 0.1902. We're ready to extract the maximum Vm and that Ks. Let's look first at Vm. This is easy because it sits all alone. This can be related to B. So B, which was 0.1902, equals 1 over Vm. Therefore, Vm equals 1 over 0.1902, which is 5.257. We're going to need this in order to solve for Ks, because the slope isn't just Ks, the slope is Ks over Vm, or in other words, Ks over 5.257. Therefore, our Ks is 16.4022 times 5.257, or 86.226. We can pull this all together to write out the total equation. That's V is equal to our Vm, so 5.257 times the concentration of S, all over our Ks, so 86.226 plus that concentration of S. Right, so this is going to be our first order equation for the Michaelis-Menten equation. We can then go ahead to look at the second order, remembering that we have this squared term. So when I go ahead and do the inversion, I end up with 1 over V equals 1 over Vm plus Ks squared over Vm times 1 over S squared. We're going to go back and do this again in Matlab, taking into account this difference. So the big difference is really only going to be changing that S term to a 1 over S squared term when we construct the inverted X piece. Okay, going a little bit faster this time, we still have our S variable, we have our V variable, but we need to have not 1 over S, we need 1 over S squared. So I'll save this in maybe S2, and I can put this in here as 1 dot slash S dot caret squared, right? So element by element, take 1 over S squared. Right. Then I'm ready to do my polyval again. I can set P equal to polyval. We've got our S2, that's our X, our V1, that's still there. And then we still want that first linear term. So we just put in a 1. Oops, sorry, not polyval, polyfit. And we end up with our 2 new variables coming out of P, that first variable, or that first number again representing the slope, and that second variable representing the intercept. Let's go back and convert these slope and intercept into the constants that we're actually looking for. So here we are back. Just as a reminder, we had those p-values of 19.3760 and 2.4492, where this was our slope and this was our intercept. We can now convert them using the same idea before, where we can relate our slope to 1 over Vm. We can relate, our intercept to 1 over Vm, and we can relate that slope to that 19.6. So once again, we have Vm is equal to 1 over the intercept. Just flipping that, that gives us a maximum velocity of 0.4083. And then we can rearrange this other equation. So m equals 19.376, which is equal to Ks squared over Vm. So this is Ks squared over 0.4083. Rearrange this, we get Ks is equal to the square root of 19.376 times 0.4083. Do out the math. This gives us Ks of 2.8127. Now that we have all this, I can put it all together in our equation that we're interested in. So our velocity is equal to 0.4083 times the substrate concentration squared, all over Ks squared. Well, that's 2.8 squared, which ends up being 7. Which ends up being 7.911 plus that concentration of S squared. So let's see how we did. Here on the top, we have the transformed model. You can tell because I have a 1 over the substrate concentration here. If I just look at this top half, I can see that I don't look so bad, right? That linear fit looks somewhat decent, right? And it's only though when I go back to my untransformed model, that original model, that we see, particularly out here at the end, I don't fit very well, even if I fit sort of okay down here. Let's see how I'd look with a second order model. Here, even in the transformed case, which once again you can tell by this 1 over S squared term, I have a much better fit. That black line, that linear fit, is very close to every single one of my points. And indeed, when I go back to the original model, so I substitute those values into that Michaelis-Menten equation, I end up getting a fit that's very good across the whole board. Hopefully this example has illustrated not only how we can use Matlab to solve polynomial fitting problems or linear fitting problems using polyfit, but also how we can transform nonlinear equations into linear equations, and we can get very complex equations we can solve for very complex equations relatively easily. With that, I want to wrap up. So just as a review, we've covered some basic statistics talking about means and variances, and then we started talking about how we can use means and variances to calculate slopes and intercepts of lines based on minimizing the error or minimizing that variance. We then were able to determine those intercepts and slopes and determine the error and our estimate. Lastly, we performed equation transforms to linearize nonlinear equations and then used Matlab to perform regression. I look forward to sharing some of these hands-on experiences in Matlab with you in class. All right, have a great rest of your day.